Hello and welcome to this video in which we are going to derive the functional or explicit relation for the Fibonacci series. Just a recap of what happened and what we have discussed in the past. We have discussed that Fibonacci series, like every other series, can be represented either by a recursive relation, which means that the next number depends on the numbers that happened or that have already been positioned before, or we can also have another relation, which is what we call the functional or the explicit one, where the number at the nth position depends on the index n. That means we can have, say, this 5 to be dependent on where it's occurring. Incidentally, it occurs at the 5th position. So we have to figure out what that relation is, and if we do that, we get the functional or explicit relationship for a Fibonacci series. So that is what we are going to do. Now, we are going to assume that we know the recursive relation for a series. Then we're going to employ a method that we described in the previous video called the method of generating functions. And using that, we will break it down into the generating functions of power series. And from that, we will explicitly find out what the coefficients of the nth power of a variable would be in that case. And that would invariably give us the nth Fibonacci number. And hence, we would have figured out the function. Okay, so let's move on. Okay, so here we have fn equal to fn minus 1 plus fn minus 2. And the numbers that we are going to say initially, we're going to put two numbers, that is f0 and f1. We'll call f0 to be 0, and we'll call f1 to be 1. And based on this, we will derive the remaining series, which is f2 will therefore become 1, f3 will therefore become, well, 2, and f4 will therefore become 2 plus 1, which is 3. Similarly, f5 would become, well, 5. Okay, and then it follows like that. Now, this is a recursive relation, which is just this. And the first, as mentioned in the first step, we will have to figure out the generating function for the series. So we will find out the generating function, and let's call that g of x. Okay, and we know by definition the generating function is defined as the summation over a variable or index, say n, starting from 0 all the way to infinity, and the terms are as follows: f sub n, x to the n. Okay, so this will help us get an analytical form for the generating function. Okay, so now what we notice is that we can employ this formula to kind of expand this out. But note that this formula, that's this one, the recursive formula, is only valid for n greater than or equal to 2. Okay, only for n greater than or equal to 2. And why is that the case? Because, remember, for a recursive relation, we need a few numbers before. And as this recursive relation employs at least two, well, it employs two numbers previously that have already been described, only then will you be able to guess the one that appears after that. You need at least two numbers in the series to start with, which are the following, f0 and f1. So that means that we can only employ this formula for n equal to 2, 3, 4, and 5, and that will give us numbers ahead of that. Okay, so that means what we can do is we can actually split this relation. So we can call this g of x, therefore becomes, just expand this out, f0 x to the 0, f1 x to the 1, and let's call this fn x to the n, but n now goes from 2 and all the way to infinity. And why is that the case? Because we've already included the indices before 2, that is 0 and 1. Now note, f0 is 0, so that's a 0 there. Right, so this term just cancels out. f1 is 1, and next to the 1 is just x. Okay, so that gives us x plus, now this is the summation there, and remember, we can always write fn here as n minus 1 plus n minus 2. Alright, what does that mean? Is if we expand this term out, then when we multiply this by x to the n, which is this term, then we have this relation, this expression rather, and this is what we get. Okay, so this term expands as, this entire thing expands as the following. And note that if we sort of take one power out, but we multiply it by the same power there, and we take two powers out here, and we multiply, we take two powers out and multiply two powers there, we do not change anything. Okay, so we're going to make use of this way of representing this. So we're going to make use of this, and then we're going to make use of this. And we're doing this because we want the indices that appear on n and f to be the same. Why? Because that gives us a relation very similar to the generating function itself. So we have the following: x f n minus 1, x to the n minus 1. In fact, the summation can kind of come inside, and we are left with this. But now, n minus 1 goes from Well, n goes from 2, remember, so n minus 1 always goes from 1. And then it goes to infinity. And similarly, we have x squared, that's not a cube, and we have the summation. And we have the following term, minus 2, which is just this term. But since n goes from 2, n minus 2 goes from, well, 0. Okay, so you just subtracting 2 from both the sides of this equality, and you get that, and it goes all the way to infinity. So now what we do is we make an observation. Well, the observation is as follows. So g of x appears on the left-hand side, which is this, and we simply write it down like that. But note what this number is. Well, this expression is just another way of writing a different form of the generating function itself. But note here, n minus 1, or the indices, or the coefficients, or the powers begin from 1. They don't begin from 0. Okay, that's important, because what this gives us is the generating function for this series. Okay, it doesn't include f0 term. But what is the value of that f0 term? Well, that's 0. So neglecting it really doesn't neglect anything. We're still working with g of x. So that means this is effectively g of x minus f0 x to the 0. But since f0 x to the 0 is 0, we're just left with g of x. Okay, so that's been sorted. Similarly, we have x squared, and in this case as well, note that here the series actually begins from 0. So n minus 2, or whatever variable this is, you can just call this k, you can call this k as well, and you can call this n minus 2 thing as k again. Now, k goes from 0, f to the f sub k, x to the k, which is basically a generating function in its entirety. In this case, we're not even subtracting any term, we're including all the terms, all right? So this is what we get. Now, this helps us get an interesting analytical or functional relation for g of x. And what that gives us, if we take all the g of x's terms on the left-hand side, we get this minus this square, and that happens to be the remaining x. So g of x therefore becomes x divided by 1 minus x squared. All right, so that has been the analytical description for the generating function. That's good. Now what we have to do is we have to split this into partial fractions that helps that sort of resemble the following format. They resemble the format of a divided by 1 minus a prime x plus b divided by 1 minus b prime x. Okay, so if we do that, we get this generating function to be a sum of generating functions of 2 GPs. Okay, so that is the idea. Now, why are we sort of differentiating or splitting this into just 2 GPs? It could also have been 3 GPs or 4 GPs. You know, they could have been 1, 2, and another term right there, described by, say, the variable c. You know, it could have been that case as well. But why 2? Well, the answer to that is, if you notice, when you split partial fractions, they depend on how many roots the denominator has. And in this case, we can see that the roots of the denominator here are just 2, right? Max 2, right? They could have been just 1, and that number could have repeated. So if that means there are 2 roots, that means there can only be 2 partial fractions. Okay, that's one of the property of how many partial fractions a complicated fraction breaks into. So that's something we're going to employ. Now we're moving on to step 2. And let me get rid of this. Okay, so we all have that in mind, that generating function happens to look like x divided by 1 minus x squared. All right, now we have to split this. And the one way to split this, and this is step 2, split g of x into generating functions of 2 GPs. Now there's a lot of G and P happening, and so this is generating functions, and these are geometric progressions. Okay, just clarifying that out. Okay, so we have to split this. I referenced something to do with roots. That means we have to take into account what the roots of the denominator are, right? So if we take the denominator as this, which it is, and we equate it to 0, we get, by solving this, we get the roots. By solving this expression, this relation, we get the roots, okay? And one way to do that is just multiply by minus 1. So you have the a term, you have the b term, you have the c term, and c is just minus 1, b is 1, a is 1, and you use the roots quadratic root formula, and you get the roots to be minus b, which is minus 1, plus minus root b squared minus 4ac. Now b squared is 1, minus 4ac is just minus 4. Well, that makes it plus 4, so that makes it plus 5. Okay, and we divide that by 2 times a, and what is a? That's 1, so that's 2. So we get 2 roots, they're different roots, and they differ by root of 5 by 2, and so what we can express this as, and therefore this can be represented as x minus root 1 and x minus root 2, x root 2, okay, so these are just the roots. We just have to put this into positions of xr1 and xr2. Okay, so let's let's kind of work with a few numbers, or let's write it explicitly. Okay, so this expression therefore can be represented as x minus, what's the first root? Well, that's 1 minus root 5, so that makes it plus. And the other term becomes x minus, well, that's still plus, but there's a negative sign there, and you have by 2. So that's the expression that's appearing in the denominator. Or is it? Well, note we multiplied this by -1, okay? So we have multiplied this by -1. But the actual expression is actually the negative of this, so we have to take into account that. So this is the actual denominator, so this happens to be the denominator, this expression, okay? So we work with this, and what we do, for just the sake of simplicity, we call this number phi, and we call this number phi cap. All right, you understand why we're doing that. So this becomes x plus phi, and then this becomes x plus phi cap. All right, so it just kind of simplifies things out. But what is the significance of these numbers? If you notice, I have chosen, if you notice what this number is, this is actually what people call in mathematical literature as the golden ratio. And it's exceptionally something that's seen everywhere, you know, and that is very interesting because it comes up from a series, the Fibonacci series. And that's really interesting because many buildings have their columns and their roofs in this ratio of the golden ratio, and that makes it a really interesting number to explore. It's something like a pi, or something like the logarithmic number, which is e. Okay, so we won't go into that, but for now, let's just think of this as a specific number. And also, the phi cap number as another specific number, but the interesting properties that come about when we consider both of them is the following. Now, if you notice what phi cap is, which is just multiplying both these numbers, you do the math and it would turn out that these are -1, all right? So that's fairly simple to see, and I urge you to work that out yourself. And the other thing that we notice is that if you subtract both of them, that is, if you subtract this from that, you actually get root of 5. Okay, well, that's a 5. Pardon the handwriting. That's 5, root of 5. So these are kind of interesting things to notice. Why? Because we will employ them eventually. All right, so that's something that you can obviously have a look at. Now, what we are left with is the following. So we have g of x happens to be, well, there's a minus on the denominator, so we take that on the numerator. We get minus of x, and this is something like that. And this is something like that, right? Fair enough. That's exactly what the expression is. Now, let me just get rid of this for now. And what we do now is to split this. So, time to split. What we are going to say is that, okay, this number is going to look something. First of all, yeah, remember one thing. I wanted to split my my g of x expression into the form of lambda divided by 1 minus lambda prime x. All right, so notice one thing. What is the coefficient? In the denominator, what's the coefficient of x to the 0 term? That is 1, and that's important. Why? Because that's how the sum of geometric series are. They always are the form a upon 1 minus r. You will not see a number other than 1 there. So we clearly need the coefficient of the coefficient of the x to the 0th term, or the constant term, to be 1. And how do you do that? Well, by noticing these two terms, if we divide this, let me choose another color for this. If you divide this by phi, we effectively divide this by itself, and we make this 1. And we do the same thing here, but with phi cap, we also get a 1 here, right? Don't worry about what's happening to x for now. We can work that out later. But we are dividing this by a number. Okay, that's phi cap. That also means we'll have to divide the numerator by that same number, which is phi cap. Alright, so this doesn't change anything. And from the properties we discussed before, well, we said that this is just -1, so this cancels with the -1 there. And notice that 1 by phi happens to be minus phi cap, and 1 by phi cap happens to be minus phi. So that is something we can employ here and there. Okay, so we get the following: x divided by, so this is 1 minus phi cap x. That's the first factor, and the second factor is, well, that's a phi x. All right, so that is what our our generating function now looks like, where the numbers phi and phi cap have been specified by these two relations. Fair enough. What we do now is we have something to work with. Now what we do is we do the splitting, the proper splitting of these numbers into the form a divided by, say, 1 minus phi prime x plus b divided by 1 minus phi x, okay? And the way we do that is we notice that the numerators have to match because the denominators do match. That's simply the product, and that appears here. So in order to evaluate what a and b would be, we have to equate a relation to x, which is the numerator there. So that means a times, we multiply this fraction to that, or this denominator to that, get that, plus b times 1 minus phi. This is just x, okay? So that's cool, that's really nice. What we can do now is we can equate the coefficients. So we notice that there's an a plus b that appears here, and there is, well, no constant term that appears there, but there's just an x to the 1 term, all right? And similarly, for the x, the coefficient of x happens to be, well, a phi, that's a minus, and minus b phi cap, okay? So that's something that we get. What can we do with this is that we must equate this to the 0 term there, because the constants should be the same. That gives us a equals minus b. If this is 0, a plus b is 0, a equals minus b. And this must be equal to the coefficient of x, which is just 1. So now we employ this relation, we get this minus b, that is 1. But note, what we found out earlier was the fact that minus b itself is a. So this just becomes plus a. Okay, so now we take a common out, and we are left with this minus that divided equal to 1. So a happens to be 1 divided by this number, which is just negative root of 5. Similarly, b happens to be, because of the relation there, plus 1 by root of 5. So that's it. You have the numbers, you have the splitting, you have both the fractions, all right? Time to be excited now. And what we get now is that we can simply just get rid of a and b and write them out in the following way. So let me just change the color for that. This is the denominator, and those are real lines. Okay. Yeah. So what we can do now is we can simply substitute for a and b. Remember, a was here, so what that becomes is minus 1 by root of 5, and b was there, which was just 1 by root of 5. Okay, so all this to get something of the following format. Okay, so these two are the numbers for the generating functions, and they happen to look exactly the way like two generating functions for geometric progressions look like. What can we conclude from this? We conclude that the Fibonacci sequences generating function g of x is actually made out of two geometric progressions. One with the common ratio, which let's call it C sub r, CR, is actually phi cap, and the other is made out of a geometric progression with a common ratio of phi. All right, so that's interesting. So the Fibonacci sequence happens to have these two contributions. And what are the constants? Well, the constants are just these. Okay, so we have to multiply them in order to get sort of normalize the generating function of the Fibonacci series, part of that. Okay, so what we have now is that if you have to evaluate the coefficient of x to the n in g of x, we know from a very definition that is just f sub n, okay, from this relation. What that means is that would be equal to the coefficient of x to the n in a GP with common ratio phi plus, and we have to multiply that, wait, not a plus yet, we have to multiply this with what was the constant term for the generating for the GP with the common ratio phi. Well, that was plus 1 by root 5, and then we have to add that to the same thing as what we have there, the coefficient of x to the n in the GP with the CR phi cap, but we have to multiply this by negative 1 by root 5 because that was the value of a. So what this gives us is that, okay, in a GP, the coefficient of x to the n itself is just the common ratio to the n, and that we must multiply by root 5. Similarly, we have phi cap to the n, and we multiply that by 1 minus 1 by root 5. Therefore, and this is the final bit, the nth Fibonacci number appears to be, if you take 1 by root 5 common out, phi to the n minus, so phi cap to the n, where phi equals 1 plus root 5 by 2, the golden ratio, and phi cap is like the conjugate golden ratio with the value as follows. Okay, so that is your analytical or functional way of representing the nth number in Fibonacci sequence. So this is clearly different from the relation we started with, which was, well, we have it already, which is the fact that it depends on the previous two numbers. And at this point, it's a great exercise, and I would urge you to do that you can actually use this to obtain that. Okay, do that, convince yourself that they are the same, and you'll be really excited because you can employ this function for this methodology for many other recursive relations, not just the Fibonacci sequence, but many other ones. For example, if you, rather than having plus, you could have had a negative sign there, or you could have had a multiple there, you could have had another multiple there, and you could have still gotten some other relationship using the same methodology. So I hope this video made sense, and I hope it helped you to understand how you can go from recursive to functional forms and back. And this is just an example where we took the Fibonacci sequence and got this analytical or functional or explicit relationship. So all the very best and have fun.